Thanks, Rick. I'm going to share my screen, I think. Yeah. Is it working on your side?
Yep, that's good.
Yep. Cool. So, yeah, good afternoon, everyone. It's a pleasure to be in Ailleres. I'd love to be there physically rather than virtually. So just for the occasion, I put two photos there. The top one here is me looking at the Marimo slide, I think, in 1997. And the bottom one is consequently from the field trip we did with the Geoscience at the time. I built a explicit 3D model of the mid-aqueduct culmination. So the red bit for here is Wimborough granite coming out. So the topography is currently right through the middle of that granite intrusion for here. It took me a while to build that model, and I believe that Rick built it with no previous experience with Loop, built it in probably a few minutes or a few tens of minutes. So I'm going to talk about Loop and what is Loop, why we have Loop, and then Mark is going to talk about Map to Loop, which is an automatic way to analyze geological maps to augment data, if you want, and produce that augmented data is then fed into LoopStructural, which is a library that Laurent developed. And this is actually the structural modeling engine. So there is a pre-processing phase with Map to Loop, automatic extraction of knowledge, if you want, from data and servers. And then the LoopStructural is the bit that does the 3D geometry. So why do we have a new platform? It's really because in 2015, I think it started, the idea started way before. Mark and I have been whinging about, the GoCAD, the Leapfrog, and et cetera, that they're very hard to use in hard rock terrains. And then Chris Bygram came and talked to us and said exactly the same thing, and said, and I would be happy to found a research group to develop a new platform to do this. Since then, so we started the real development of the software in 2019, so about 2 years ago in a week. And since then, we've added a lot of extra bits to just the structural modeling engine. We actually looked at a lot of work upstream, if you want, which is looking at extracting knowledge and using all the data and information and knowledge we have in our database in geological surveys, but in companies and in the great literature, et cetera, et cetera. Then there is the pillar, which is called the geological and geophysical modeling engine, where we try to integrate geology and geophysics from the beginning of the workflow. So we don't want to use geophysics just to falsify some of the model at the end of the modeling workflow. And then we're also very aware of uncertainty, and this is separated here as almost a downstream time post-processing module, but the uncertainty is actually considered throughout the entire workflow. So we need to capture uncertainty in the input data. We need to capture the uncertainty in the modeling method and algorithms. And then we also need to do something with the uncertainty. So that's what Rick was talking about as an introduction. We need to use the uncertainty to tell us where to go next to acquire what type of data and where, and to maximize the reduction of uncertainty. So this is really the aim of Loop, is to produce a package that will automatically, reproducibly and objectively snatch all of the data that are available on servers, build reproducible models, and then assess the uncertainty associated with those models, so data uncertainty, but also algorithmic uncertainty, to do something with it, so to tell us what to do next, and also to provide a system that allows decision makers to make decisions rapidly, and also to change those decisions rapidly because we are able to actually test those decisions very quickly. So just quickly, the Geological Knowledge Manager in one of the pillars is developed by Boyan Broderick and people at Geological Survey of Canada and also Geoscience Australia. They're looking at developing ontology of geoscience to capture knowledge in a clever data structure. And then there is another part, which is the Map to Loop library developed by Mark Jessel at UWA and Vitaly Ogarko, sorry. And it's really about extracting topologies, so extracting stratigraphic columns, for example, extracting fault networks, fault formation networks, and structural data automatically from just looking at the maps. In orange, going back to the geological and geophysical modeling. So this is an idea of encoding the structural geological rules to do the modeling, and also to develop geophysical inversions that are formulated on a deformable geological model. So, and if you can deform a geological model during inversion, that means you can keep the implicit formulation of the geological model and run the inversion for that. I'm going to show you some examples of that. And that's the work of Jeremy Giraud at UWA. And then the uncertainty. So you're probably familiar with the work of Mark Lindsay, looking at stochastic simulations and generating ensembles of 3D models and analyzing the variability within those models. But we're also moving towards more and more towards a Bayesian approach to the modeling. So looking at the prior of the structural data, if you want, and inverting the structural data to create geometries, and then informing obviously the uncertainty as we go. So lots of words. Let's look at some pictures. So yes, so again, one new platform. The current technologies, off-the-shelf technology, are not allowing us to build reproducible models. So you can build those models, but you will build one and you will stop there. We want to be able to automate the process so that you can actually run those stochastic simulations, so you can invert the geology and geophysics together to characterize uncertainty better. And at the end of the day, the ultimate goal is really to guide the acquisitions of the next piece of data that will maximize the uncertainty reductions. And Mark Lindsay is looking at this also in an economic sense, looking at the value of information. So it's not only looking at what type of data and where, but also the value of that data or the cost of that data, and trying to optimize the system to maximize your bang for bucks, of whatever the expression is. The software is open source, and because open source is a feature, and we want to adhere to the FAIR principles, so findable, accessible. I forgot now, but it doesn't matter. And we want to make sure that everybody can use the software. We have a governance, so Mark and I are not allowed to just roam and run around doing things. Lots of people are involved in the projects. People from Moscow, people from Geoscience. It's actually run by the One Geology Consortium. Matt Harrison being the representative of One Geology on the steering committee. And on the right here, I'm not going to go through the details because I'm already talking too much. These are the people actually doing the research or running the different modules of the research. So map to loop, I'm not going to talk about it too much because Mark is going to give you a demo, but the idea is, as Rick said at the start, so this is an example from the Flinders Ranges. What we have here is we have a shapefile served by the Geological Survey of South Australia with a geology in the background, and the red dots are structural measurements, so bedding information or bedding orientation. And the idea is you draw that little rectangle, you press a button, and in about 10 minutes, you get a 3D model that looks like this. So as I said before with the Metacritic examples on the title slide, building this model on the right here, building this model on the right here would have taken probably about 3 weeks of a competent 3D modeler. You can now do this in 12 minutes, and it's reproducible. So you draw the same rectangle, you get the same model. And so you can run simulations, you can vary, you can introduce noise into data, you can do all these things and run stochastic simulations, and it doesn't take too long to generate a model. The idea of the pre-processing loop or pre-loop, if you want, is basically to be able to access or talk to all the different databases and servers available in our surveys at the moment. And then being able to, for example, manage projection systems, look at formatting the data in a format that Loop can actually digest, looking at upscaling and downscaling of data. Sometimes there is too many data points. Sometimes there aren't enough. So you actually need to know that as well. And it's really a question of extracting knowledge out of geological maps, for example, or drill holes. And one of the easiest example is to extract the topological relationship on the map, which gives you the fault network, give you the fault formation relationships and the stratigraphic column. And of course, we can vary those because this is not always set in stone. So the idea is eventually to be able to run simulations also on the topological representation of the geology. So going back to the knowledge manager, the work of Steve Richards from his ex-USGS and Boyan Broderick, Geological Survey of Canada, is basically encoding into a data structure the principle of geoscience. So the principle of cross-cutting relationships and the principle of superimpositions. So this is tested at the moment. They are in the phases of testing it, and we need to now integrate it and link it a bit better with Map to Loop. And Map to Loop is really about, I'm going to pass this one for time saving, but Map to Loop is really about, on top of the topological relationship, is looking at extracting geometrical and structural informations out of the maps. So for example, here we have two diagrams from a map in the Pilbara, where the dots represent, and the color on the dots represent the thickness of a given formation. So you end up with information for per formation and distribution. So probability density functions, if you want, of thicknesses for each lithologies. On the right-hand side here, you have something very similar. It's an estimation of the fault offset, so the apparent fault offset or the minimum fault offset on those faults. And again, you end up with a probability density functions of those offsets along the faults. So you can start thinking about how we can use that type of analysis to create a Bayesian inference and be more or be less deterministic in our modeling approach. So we've developed demonstrators for all the states in Australia, and I think this is what Mark is going to demonstrate, and I think this is what we're going to try to do together with Lachlan a bit later. And these are the areas where Map to Loops works, because Mark is going to detail this, but Map to Loop works everywhere. You will get a model everywhere as long as you have the right data, but the model may not be realistic, or the model could be complete rubbish. So we're not replacing the geologist, but we're empowering the geologist to think about geology rather than thinking about what button they need to press next to build that model. So we're taking away the technological complications of building 3D models. So how do we do this? So this is now looking at LoopStructural. So this is developed by Lachlan Gross during his PhD and now during his postdoc. And we basically developed the concept of the structural frame. And the structural frame is a coordinate system that's defined by the finest train ellipsoid principal directions of an event. So a fault is one event, another fault is another event, and a folding event is an event. For example, an intrusion event is an event. So for each of those events, we can define those structural frames. And for example, for folding, one direction would be perpendicular to the actual surface, one direction would be along the fold axis, and the third direction is perpendicular to the two, and basically, roughly in most cases, parallel to the extension direction. Once you can interpolate those directions everywhere in the volume, so fitting on the data, you can actually interpolate the entire fold profile. You can interpolate the entire fold profile, sorry, and the entire fold geometries through the volume. And similarly for faults, so they're defined by a damage zone as an ellipsoid, and then the structural frame is defined by the slip direction, a direction perpendicular to the slip directions within the fault, and then a direction perpendicular to the fault. Of course, these parameters are not things we measure in the field. It's very rare that you can actually measure the direction of slip and the amount of slip on a fault. Same thing for the folds. Well, we fit them with a Fourier series. We never measure Fourier series coefficient in the field because they're not there. But we could measure the wavelengths, for example. All these can become parameters that we can use in a Bayesian inference to actually model a faulted fold. And I'm going to show you an example of that in the next few slides. We've also made progress on modeling intrusions, again, using structural frames. And this is the work of Fernanda Alvarado doing a PhD at Monash with Lachlan and I. And she's actually adapted a method developed by Ailleres in 2010 to model or to simulate karstic systems. So the idea is to develop a skeleton, which will be in the middle of your intrusion through here. And once you've got your skeleton, so based on data, obviously, once you've got your skeleton, you can then simulate a thickness for the intrusions if you want, using different ways of doing this. And you're then able to, for example, model a dike transitioning into a seal, then stepping up into another seal, etc., etc. So we should be able to stochastically simulate intrusion networks and then also backfitting them to actual observations in the field, including orientation observations. So thinking about the Bayesian modeling, so loop structural is time aware, which means that we model the youngest event first, and then we go backwards in time. This is not really doing restorations, although at the back of my head, I think we do restorations, but let's not think about that for now. But we model one fault after the next. So faults cannot happen at the same time. So they have to have at least a millisecond of activity of lull in between both faults. So one fault after the next, and then we measure the displacements all together. So we add all the displacements of all the faults. If they interact, are added together. So here is an example where we have a folded stratigraphy. So this is here the actual trace of a antiform, and we have a fault here, and the arrows, of course, are not correct. They're not actually kinematic arrows. They're just telling you that we're going to restore the displacement of the fault first. So this is what we're doing here, and then once we've done that, ignoring the fault, we can then model the fold profile. So this is done through some graphs that Laurent invented. On the left here, you have, on the left here, you have the fold profile. So this is showing you what the fold axis is doing in 3D space. And at the bottom down here, you have the fold profile. So the shape of the fold, as if you were looking down plunge for each of these locations. So you're actually doing what structural geologists do in the field. They look at the structures down plunge and estimate the shape of the fold. On the right here, we use semi-variograms on the angular variations of the folded foliation or the folded fold axis to estimate the wavelengths. It's really a guesstimate to actually seed the system for the inversions. So the idea is to feed a profile on the fold axis. Oh, yeah, sorry. So of course you have the data as is now. Then you have the data once we've restored the fault. And then once you've done that, you can feed a profile on the system. It changed a little bit. I'm sorry, this is the scale changing at the bottom. And once you've done that, you actually can interpolate throughout the entire model a faulted fold. But there are a lot of unknowns. So for example, we don't know as I said, we're fitting a Fourier series on the fold profile. So we don't know the coefficients of the Fourier series. We don't know the wavelengths of the fold, and we don't know the slope of the fold. We don't even know the direction of the slope of the fold. In this case, we've assumed it was vertical. But you can very easily, you can run Bayesian inversion. So all these parameters become your priors, and you then sample the model space if you want, defined by the different parameters values, to find models that are actually going to fit both the equation of the fold, so the Fourier series, and the fold frog. So down here, you have an example of how the model space has been sampled. So for the different coefficients of the Fourier series, so C0, C1, C2, and also for the fold wavelengths. And down here, we also have the fold displacements. So you're looking at density plots of where the system has sampled our parameter space. And for each of those parameters samples, you can also look at what the fold profile would look like in our what we call the S-plot. And of course, you can realize very quickly that away from data, your uncertainty, or if you want the width of that curve, is actually increasing dramatically, which tells you that the system is very uncertain away from the data points as intuitively as we would think intuitively, obviously. But anyways, this is a proof of concept to show you that we can use Bayesian inference to invert geology from data, from geostructural data, and of course the maps. A quick word on the geophysical aspect. So this is the work of Jeremy Giraud at UWA, and is basically trying to integrate. So at the moment, he's been focusing essentially on gravity data. He is trying to start working also on magnetics at the same time, but he's trying to integrate geological informations and petrophysical data, obviously, into the inversions algorithms. And he's moving away from the typical technologies and trying to use deformable geology, so where you take an a priori geological model and you deform it instead of instead of rasterizing it, if you want, or voxelizing it, and then you've lost the connectivity between the different cubes. And it's also using label set functions to do the inversions. So the idea is to use as much information as we can, including potentially the output of the geological modeling as the lithological probabilities or uncertainty value for within the volume. It's also looking at doing cost gradient constraint inversions, so joint inversions, guided inversions, and also using the posterior of one type of inversions as a prior model for the next data set to be inverted. So it's really clever how he's doing this. These are the product you get at the end, and of course, he's also done a lot of work to try to recover geological models from the physical property models. But if he keeps going towards that concept of deformable geology for inversions, we will keep the implicit formulation of the geology, which is, for us, this is very important because that means that eventually we should be able to have a single likelihood function for both geology and geophysics. So yes, we want to use everything we can. And these are examples. So this is an example of deformable geology with a level set function. These are very simplistic, obviously, but what we're doing here, we're trying to recover the cross sections with the white outline. And this is the starting section. And over the iteration, you can see that even if you keep if you keep the formulation of the geology, of course, this is stupid geology because this is spheres and objects and regular objects, you can still change the topology of the model, which is very important here. So for example, this blob here disappears and basically is sent over there. And that is changing the topology of the model, even if we're just deforming the geology. So same concept is working on real cases. This is in the Pyrenees, again, the work of Jeremy Giraud, and this is a lithospheric inversion through here. So you got multiple layers with different, lithologies. I think in dark yellow here is a mantle, or the upper mantle, and we're looking at structures deep in the Pyrenees. And I think this is very promising because it's usually very hard to get deeping bodies through typical inversions. The other things that Jeremy's been doing, so there's a guided inversion. So he's using, so this is an example again. This is a proof of concepts. This is a cross section at the top here, where you have the color correspond to different density values, and the numbers correspond to different resistivity values. And the idea is to generate a noisy gravity field and a noisy resistivity profile, and or EM profile, and invert those profiles to try to recover the cross sections without knowing the cross sections. So this is the principle of guided inversions, where the first step is to invert the MT data first, and the MT data give you that posteriori domaining if you want. And so, for example, what's in white here is considered to be sediments. So they can have, in terms of densities, the rocks in white can have any values between 0, 110, 170, and 240. Which I don't really know what it means. Oh, yeah, so they scale in those units. In red, the MT has decided that this should definitely be basement, so the density is 300. And then in black is the uncertainty, so we don't know what's happening here. So you can then run the gravity inversions, and this is at the bottom, this is the result, and you recover the basement quite well. Because you've actually enforced it through the MT. So you're using the MT and the gravity information to recover the basement better. If you did the gravity inversions without the MT domaining to start with, you actually don't recover any basement in that part of the world here. So of course, this is not perfect yet, but as a proof of concept, I think the idea of using one data set and the result of one data set inversion to constrain the prior model for the next level of inversions, I think is very interesting. Lastly, I wanted to talk about the future of Loop. So we're going right now for a second phase of funding through the ISA, but we're also looking at the industry, at an industry project to do a resource estimation within implicit formulation of the models. And so these are the different structural frames that we talked about at the start. for the fault, for the intrusions, for the fold. And those structural frames define a coordinate systems everywhere in the model. So that means that we can calculate distances within every volume that is conformable, or that is conformable to layering and faults. We can calculate distances, which means we can do geostatistics very easily. And we're going to develop, well, very easily. I say that because I'm not going to do it. This is we're looking for a postdoc to actually do the work. But we can do resource estimation, property modeling within our implicit formulations, which means we can propagate the uncertainty of the geology and the uncertainty on the data, on the properties, for the entire resource type estimation in the 3D volume. So if I've got time, maybe I got 2 more minutes. So the funding actually goes to people. So we created 4 research positions, 3 software design and software architect positions. 10 PhD students are involved at the moment. And these are all the people we're working with. We've had a workshop in March before we had to go into lockdown. This is the last time we were happy. So we actually have sessions where we transfer knowledge and, we run workshops and all these things. These are our sponsors. And more importantly, the last slide is this is Rick actually using Loop, and I think he's captured knowledge. So the beauty of Bayesian modeling is you can capture knowledge. And I think we can see we capture something in his head down here. And this is a beautiful model at the top here. I don't know where that is from, but this is a beautiful image, Rick. Thank you very much.